Hi everyone, welcome back. And for the last dozen videos or so, we have been focusing on object segmentation. We started off by using Voronoi Otsu labeling, the traditional approach, and then we slowly moved to pre-trained deep learning model approach, for example, using Stardist. And then we moved on to Mask RCNN, where we just trained our own models and segmented or instance segmented our objects in these images. Now, what do you do after segmentation? Why are you even doing segmentation, right? In scientific images for microscopy purposes, for example, we do segmentation as part of a bigger workflow, right? You start with collecting your images and then you pre-process them, I don't know, denoise them, for example, and then segment them. And once you segment, for example, nuclei, then you go back to your original images and say, okay, wherever I have a nuclei, what else do I have in other channels, and do some sort of a co-localization or some sort of analysis. That is one type of workflow. Another type of workflow is where you have a time series of images. You have the same frame, but as time goes by, you're collecting more images. So it's almost like a video or a movie. So that's just a microscopy example, but you can actually have real life videos or movies of, for example, bubbles like the one that you see on the screen, and you would like to track these bubbles to see how they're moving as time goes by. That's another example. If that is the case, then Trackpy, this video tutorial is going to be useful for you. So please continue watching this. Please hit the subscribe button also, because next week I'm going to show an extension of this where we are going to use a combination of deep learning based, like for example, Stardist segmentation plus Trackpy to work on your own images, not just the images that I'm going to show you as part of, in fact, what I'm going to talk to you in this video is directly out of the tutorial that these guys actually provided on their webpage. We'll go through that in a minute, but I pre-digested this for you, so you don't have to spend time learning by reading their documentation. I still encourage you to read that because there is a lot more in their documentation that I cannot cover here. Okay, I have been talking for a couple of minutes. I know you want to see things in action, so let's go ahead and jump into the browser to go through Trackpy, then directly get into the coding part. So you can find them just by Google searching for Trackpy, or I'll leave the link as part of the description down here for this video, under this video, and they have various examples, and you can go through all of these. So what I am going to walk you through today is through their walkthrough tutorial, which kind of provides you an introduction of their mindset. So what do they mean by, for example, linking? What do they mean by some other terms? So it provides a good overview. So let us go ahead and do that. And one other note, if you look at their installation, for example, if you look at installation of Trackpy, they say you have to install that using Conda, and you can kind of try to do pip, but they still say we strongly recommend using Conda to install Trackpy. This is nothing wrong with that. This is straightforward if you are using, in fact, as you probably know, I regularly use Anaconda environment on my local workstation. But for those of you who work on a notebook, Colab, especially Colab, Google Colab, then installing Conda is a bit not tricky, but you kind of need a few steps in terms of how to do that. I have done a video on that topic in the past, but I plan on actually working completely in Google Colab. So any of you watching this video should be able to reproduce what I'm trying to do. So with that information, let me directly jump into my Colab notebook that I'm going to share. Look at the link down below. And you can go through this yourself. So first thing first, let us go ahead and connect to our runtime. And when we connect to the runtime, you should see a couple of things on the left-hand side. I already clicked on mounting my drive, so I uploaded the data set. And again, where do you find the data set? For this example, I am going to provide the link right there. It's a bit tough to find this. You have to go through a lot of their documentation to figure out, oh, this is where it is. I did that for you, so go ahead and click on it. And when it opens up, look at your sample data. And the one I'm going to work with is bulk water data set right there. And I think it has 300 images. It shows you the README file. that talks about, okay, these are 1 micron charge stabilized latex spheres diffusing in water. So these are, no wonder they look dark. They are not bubbles, so they're latex spheres in water, and they're recorded at 24 frames per second like a cinematic video, and the pixel size is 1 micron is 2.85 pixels. So that is the information about this data set. I downloaded this and I placed them as part of my drive, Google Drive, and I'm not sure why that's not showing up here. Let's refresh it. There you go. So I already placed it, and you should see that under data, under tracking data, and bulk water. So I did 2 things. I actually downloaded all the individual PNGs and I placed them exactly as you see right here. And I also combined them into a single TIFF file, so I can show you both ways how to load the data set. I just used ImageJ. I mean, as you probably know, I'm a big fan of ImageJ, so I used ImageJ to import all the images as a sequence and saved it as a single TIFF file. So, and you can also save it as an AVI file, right? That's another movie file. Okay, so that is background information. That is a lot of information. I know you probably are getting a bit frustrated that I am not starting the tutorial, but this information hopefully will not leave much gaps in your understanding as you go through this tutorial. Okay, now finally we are talking about the code, and first thing first, we need to install Colab as part of our notebook. And how do you do that? I have already done a video in the past, so go ahead and watch that video where I went through this in a more methodical way. But for now, I'm just going to quickly walk through the process. First thing first, I want to find out what type of Python I have. Let me zoom in. I'm pretty sure you appreciate reading it without much. And let's, okay. So I'm doing where the Python is installed on this Linux instance, because that's Colab is on our Linux instance. So it is under user local bin Python, and the version is 3.7.13. And then there's no reason to do that, but I just want to see, okay, what version, because I want to install Conda, and I'm going to install mini Conda. So let me click on this link right there, and it takes you to this page where I can actually download the mini Conda for Linux and then install it in Colab. But I don't want to install the latest one. I want to go down to Python version 3.7 and then install this version of Linux. Why? I mean, Colab natively is giving me 3.7, so I really don't want to take any other risks by going to 3.9. That's the only reason. So I just go save as. I'm not going to download. I just want to get this file name, miniconda 3 pi 37 whatever, and then I am going to use that as a file name right there. Okay. I did run this code once. I hate seeing all that. Let me clear all the outputs so we start with a clean slate. Okay, so now let's go ahead and look at my Python path. It's under environment Python. Now let's define. Let's clear the environment. So when or reset the environment, because when we install the mini Conda or Conda in our notebook, then it is going to come with a Python version. And which Python version is it going to come with? 3.7, because that's the version we say we wanted as part of our mini Conda environment. And the version for mini Conda is going to be 4.12.0, and it's going to be on Linux 86. So let's go ahead and run this line and stop talking a lot about it. And once that is done, I am going to check which Conda. And by the way, something should show up right here on the left-hand side, because it should be downloading this mini Conda to the local environment, and it should show something right there if I'm not wrong. Let's go ahead and give it a few seconds. Okay, so this is done. Maybe if I refresh, I'll see something. There you go. So the mini Conda version is downloaded right there, or you can download and upload to this location. It's up to you, but let us, in fact, I do not recommend that. Go ahead and follow this method, and now run which Conda to see where it is located. It's under user local bin Conda. That we kind of guessed that because our Python is also located right there, right? So when you do this, user local bin Python, now user local bin Conda. Why do we need that? Again, in a minute we'll see. So what version of Conda we have? 4.12.0. Go ahead and, as you always do with Conda, go ahead and Conda update, right? So we need to update Conda and then go ahead and see what version. It should be 4.12. I think the last time when I did this, it updated that to 4.13. So I think there is one version that is the latest compared to the one we had. There you go, 4.13. And Python should be exactly the same version, 3.7.13. All of this getting ready for Trackpy if you want to install using Conda. Okay, now let's go ahead and look at all the system paths right here. So we have user lib Python 37, user lib Python 3.7, blah, 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 all of this. Why am I looking at this? Because when I do Conda install, it installs the packages in whatever that directory is /site packages. So I need to add or append the site packages to this path. So let's go ahead and do that. It did append. If I run this line again, now you should see an extra one that says user lib Python site packages. Okay. For those of you who think this is too freaking basic, why am I talking? Because my audience come with various backgrounds and I really don't want to leave huge gaps in anyone's understanding. So if this is too slow, just forward a little bit, 10 seconds, 20 seconds to see if you can pick it up from there. Okay, now let's go ahead and install. We are all set now. Up to this point, we just made sure that we have Conda available. Now we can follow the Trackpy documentation installing. So they asked us to do update Conda. We just did that. Now install Trackpy and then install Pims. Pims is used to open files. And that's also by the same people, I guess, that developed Trackpy. So let's get back. And first, let's do Initially, I did both at the same time. I just want to do one at a time. And each time you do this, it asks you, after it downloads this content metadata, it asks you, okay, this is what's going to change. Do you want to proceed or not? Then you have to click yes or no. You cannot just run all the cells, walk away and come back. If you come back after half an hour, it gets stuck at this position because it's waiting for you to hit yes. Okay, again, basic stuff, but it's worth mentioning. Okay, so it came up with some stuff. Let's go ahead and scroll down. There you go. It's asking me to proceed. I should say yes and hit return and let it finish installing. And then we'll do the Pims package. Okay, so that part is done. Now let's go ahead and install the Pims. It's going to do exactly the same. Download the metadata for the package and get stuff ready, like solving the environment, and then asks us whether we want to proceed or not. There you go. Let's go down and say yes. And this is the slow part. And after this, hopefully it gets a bit fast. And if you're working on your local system, obviously no need to mention, you just have to do this once and then you have the environment set. And from that point on, just focus on the tracking part and everything. But unfortunately on Colab, of course, you have to do this every time you restart your runtime. But it is free. It gives you free GPU, so why not use it? Okay, so I just gave you the link of the tutorial that I'm going to walk you through, but I made a few changes and I am going to fill in certain information here. So let's scroll down and run these lines. So now we are actually getting into the actual application. We are done setting up our library. That's it. Now let's go down and start using it. So as usual, I'm going to use Matplotlib for my plotting. And let's go ahead and run that. That's all that's doing. And down here, I'm going to import NumPy, obviously, to handle our images, pandas, because the information, once you do the segmentation, like all the region properties and everything, is stored as part of a pandas data frame. So it makes sense to have that ready. And import Pims and Trackpy, the ones that we just installed. So hopefully everything should go smooth. This is the first time we are running it, so it's downloading. The FFmpeg for Linux right there, that helps us handle AVIs or any other movie files that we need to handle later on. Okay, so there you go. So we imported the required libraries. Now make sure to upload your data to Google Drive. I showed you that I have already done that. And I have two versions, one a TIFF stack and the other a directory with a whole bunch of individual PNGs. Either way, it doesn't matter. It's very simple to open. It's pims.open. If it is a TIFF file, let's go ahead and do that. And now it opened a TIFF file, and this is 300 frames, 424 by 640 by 3. Yeah. Or you can actually point everything to the directory where you have all the images, and with a star.png, and this will take care of opening that. Now, one other thing that we are actually doing is we defined a function called gray to convert our images into grayscale. In fact, we're not even converting images to grayscale. We are actually taking an RGB image and only reading the green channel, and we are calling that a grayscale image, and we are decorating that with a Pims pipeline. So whenever you call this gray, it applies to every image that you are actually reading as part of this this directory. So when I run this, it should be exactly same as the above line. So if I do my frames, you see 300 frames, 424 by 640 by 4, unsigned integer 8. So it's pretty much exactly the same. I'm not sure why it says 4 over there. I have to look at the documentation, but and it should also be converted to a grayscale, only a single channel. Okay, so now that you have it, let's go ahead and have a look at it. And if it shows up in black and white or grayscale, we know that yes, we are dealing with a grayscale image. The original images have some sort of a yellowish tint. Go ahead and open them when you download it. So far, all we have done is loaded our movie, whether it is a TIFF stack, AVI, whatever format. In fact, if you're working with some scientific formats like Zeiss microscope, it's .czi extension, you can still import those because the Pims directory, right? I mean, the library here also provides you with bioformats importer, so you can import proprietary microscope images. With that information, let's now continue. Now that we have an image, the next step is to segmenting this image. And this is where in the next video, I'm going to show you how you can use deep learning or a pre-trained deep learned model to segment your images. But for now, let's use the blob detection algorithm that they already have as part of the Trackpy library. So the blob detection, I think they have, yeah, there is a, go to their documentation page again to find out how the blob detection algorithm works. But this is pretty much straightforward blob detection where you give, okay, what is the minimum or average size of the blob? And this invert equals to true is because by default, this tp.locate, they should have said pp.segment, tp.segment or trackpy.segment. They're calling it locate, but fine. So that's exactly what it's doing. It's segmenting or locating the particles or objects. And they're locating particles in this image of an average size of 11 pixels. And I believe this number needs to be odd number. And invert equals to true because it's going to, by default, look at white particles against a dark background. But in our case, we have exactly opposite. Bright background with dark particles. So invert equals to true. That's the explanation for that. And there you go. And now this is a data frame. Now, once it locates, it saves all the information as a data frame. So if you just look at f.head, you can actually see what we have here is the x location, the coordinate for each of these objects that it located. X, Y, mass is intensity of that specific pixel, and size is size in, and eccentricity, I believe, signal, raw mass. I'm not sure what these are. Again, I have to go through the documentation. I only looked at what I needed, which is the frame, the mass, the X and Y. That's it. These are the ones I care about at this point. In fact, if I use my own segmentation method, I can actually use, for example, region props from scikit-image to actually extract my own parameters right here. That's why I didn't bother too much into looking exactly what these mean, because I know for my specific purposes, I'm going to use my segmentation anyway. And now tp.annotate or trackpy.annotate actually, as the name says, it annotates. It shows you exactly where these objects are on the image. By the way, we are only looking at the 0th image as of now. But when we apply this, we'll apply to all 300 images as part of this data set. So let's go ahead and do that. And there you go. That is showing you way too many circles, way too many objects, because this faint thing is also segmented as a particle. This is why I love to use my own segmentation that I'm very much familiar with, because these slight dark ones that are out of focus, maybe we don't need that. But luckily, Trackpy actually provides you with the tools to clean this thing up, which is exactly what we're going to see right now. To clean it, one thing is go ahead and plot the mass, and mass is brightness. And we can say that, okay, this is how the brightness of every particle is kind of distributed. And anything that's below certain level, we don't care. Anything above certain level, we don't care. Usually it is below. So let us go ahead and by the way, this is for the inverted image. Yeah, so we are looking at dark background, bright pixels. So anything that's below, I'm saying that's too faint. Let's go ahead and remove that. And that's exactly what we are trying to see do here. So we are locating them in that specific frame, exactly same as before, except we added another parameter called min mass. There is like maximum mass. There is a whole bunch of other things that you can set to filter things out. I believe you can also set up a threshold saying, hey, almost like Otsu type of threshold, just only threshold the brightest ones. So let's put a minimum mass of 20. And now let's go ahead and annotate to see how the image is. That's, believe it or not, far fewer compared to what we have here. This is much more busy compared to what we have here. There are more ways to filter that out. Again, we'll see that in a minute. But now that we located this on one single image, let's go ahead and apply that to all 300 images in our time series. And the way you do that is use exactly the same thing. Sorry, right there, tp.locate. Instead of frames 0, I am going to say frames all the way from 0 to 300. With a minimum size of or average size of around 11 pixels, min mass 20, invert equals to true. So exactly the same, except I'm giving a movie here or multiple frames here instead of a single frame. So let's go ahead and run this. Pretty fast actually, as you can see. And it's reporting number of features it found per frame. So let me be quiet for now and stare at the screen until it's done with all 300, and then we'll continue. Okay, so now that it is done, we are ready to link the features into particle trajectories. What does that mean? In fact, we should have started by looking at the image right here. And these are all the 300 individual images as part of our time series. So if I just go ahead and hit play, hopefully you should be, let me just drag this so you can see how the objects are moving. Yeah, this is exactly what we are trying to track. Now, how does the tracking algorithm work? Well, it looks at this specific object, for example. Is there a way to zoom in? Let's take this. Makes it easy for us to understand. Okay, let's keep it right here and keep an eye on a couple of these objects, right? I mean, these ones. So if I move it between the frames, they're actually moving a little bit. The way the tracking algorithm works is, okay, compared to the previous one, I'm going to look at plus or minus these many pixels in the next frame, assuming that the same object is going to be within that region in the next frame, right? So if all of a sudden, if this object right from somewhere else jumps into this position, there is not much we can do. Then there is chaos. Then everything's moving in all directions. We have no clue how to track. The only way we can track is making an assumption that, okay, so these things are within certain distance as I move from one frame to the other. That is the key assumption. Now, again, there are a couple of ways that you can, if you're trying to predict where the objects are going to be, then if they are non-Brownian motion, then you can try to do that. Brownian motion it's kind of random motion, right? The object is moving in not a predictable motion, so you cannot kind of predict future. But if they are moving with a specific mean velocity vector in certain direction, then you can actually predict in future. Quick overview of how the tracking is going to work. With that information, now let's go down to link features into particle trajectories. This is exactly what that does. So we need to provide two different parameters right here. How far can they go? So it looks at that neighborhood only. And also sometimes when you have objects in the edges, like, I don't know if that's happening in this case. Let's go ahead and zoom out, zoom in a bit. And if you look at some of these objects in the edge, for example, the one right there, as it goes by, you see how it went out of the frame right there, and then it probably comes back. Well, in this case, it's not coming back. Sometimes objects can go out of the frame and come back into the frame. So this second term, memory, is all about how many frames do you want me to remember that a particle existed in the frames before, right? So that's what memory is. So this is our data set, our movie. This is the number of pixels for the neighborhood, and this is the memory, how far. So this is how it's going to link and let it do its stuff for all the 300 frames. And once it's done, we can look at, again, that is going to be a data frame. So let's go ahead and look at the data frame right there. Exactly the same data frame, except in this case, it added extra column called particle right there. So that's it. So that's how, again, go ahead and open the entire data frame to have it, or save it as CSV so you can go through it and understand exactly how that is organized. Now, once you have this, you have all the data that you need to extract the information that you want. First thing first, you can filter spurious, if I can say it right, trajectories, which means sometimes the objects are seen only for a few frames and they don't exist anymore. You can kind of choose to not include them. So for example, here we have given a value of 25 for, okay, how many frames? And then if it is not at least 25 frames, then go ahead and remove that. This significantly decreases the number of particles that you have. So we are going to print out before and after. So if I do that, you should see some 13,000 before and only 1,500 are remaining. These are the ones that are consistently showing up before and after. And if you kind of plot that, another way of filtering. Yeah, this is basically filtering right there. And you can also filter based on the particle's appearance. Like remember, we have a whole bunch of parameters associated with each of these. And again, if you use region props, you can even get more parameters. But in this case, we are plotting size versus mass. And then we can say, okay, some of these I really do not want to be included. And you can actually go ahead and add your own rules. Again, this is basically a pandas data frame, so it's up to you, whatever you want to do. So here we are saying, okay, anything greater than 50 in terms of mass, and in terms of size less than 2.6. So less than 2.6, greater than 50 right there. Go ahead and eccentricity apparently less than 0.3. There is a reason why they included eccentricity over there. So that is what we are including. And when you plot it, you can see that we now have far fewer objects compared to where we started off with. Again, these are all filtering options. You can choose all objects if you want. It's up to you. Now trace the trajectories. Now when you plot this is the fun part, right? And we like to see, we are all visual. And we like to see how the trajectories are. And by the way, you can add original image inside plot underscore trajectories. If you put, I think, original image overlay equals to true or something. Again, look at I'm going to cover that in the next video, but look at the documentation if you can't wait until next video. Then it overlays the trajectories onto your original image, showing these squiggly lines of where the objects are moving. Okay, now, I'm going to just go through a couple of analytical stuff that you can get out of it. For example, well, not yet. In fact, if you look at this, how do we know that there is no systematic drift? If there is a systematic drift between all of these objects, because the stage is moving, I don't know, optics are changing for whatever reason, it's not actual drift within the objects. You want to subtract that from each of these. That's exactly what we are looking at here. So it can compute the drift, and you can actually see if there is any drift. As the frame goes by, as the time goes by, there is a systematic drift, in all the particles, in all the objects that we have recognized right there, in X and also in Y. So we need to subtract this drift from the actual drift X and Y values for each particle as a function of time. And that's what the subtract drift does right there. And then now you can plot the trajectories, and now you will see that it is not as bad as is showing up right here, right? So here it's a lot more movement right there for some of these, and now you come back and you see it's not the same movement. So if there is a systematic drift, there is a way to correct that. Now let's go ahead and analyze this. So there are a few things that you would like to get out of any of these tracking type of experiments. One is mean square displacement, and that is calculated by IMSD, mean square displacement. And there is also another term that you can extract, which is ensemble mean square displacement. So first, let's look at the individual mean square displacement. This is basically your, let's go back, this, the trajectories. And the second parameter is your pixel size. Again, in this case, it's 100 over 285 microns per pixel. We already established that from our metadata, and 24 is just 24 frames per second. So let's go ahead and run that, and you can look at the mean square displacement once that is done. Okay, so now we are plotting it as a function of lag time. Again, if you come from tracking background, you probably know exactly what we are talking about. So go ahead and, if not, go ahead and look at the documentation to get better understanding. The ensemble mean square displacement, it's used exactly the same way, right? I mean, it's again, instead of IMSD, I changed it to EMSD. That's pretty much it. And then we're going to plot, and this is going to be a nice straight line or dotted line because we are doing the log plots right here. So in a log plot, it's going to appear as a straight line, and we just need to fit this to the power law because we are fitting it in the log space, and it gives you exactly your mean square displacement parameters right there, and that gives you some information about how these objects are moving, about probably the viscosity of the material in which these objects are moving, for example. So this is a quick, well, I say quick, it took a bit longer than I thought it would because I went through the process of installing Colab, installing Trackpy and everything. Stay tuned for the next one where I am going to take a bunch of nuclei images and segment it using Stardist and use pretty much the same approach. Subscribe if you want to be notified when that video gets uploaded. Thank you.